Hey everyone, welcome to this highly focused explainer. Whether you're drafting complex aerospace components, inspecting automotive assemblies, or writing out CNC toolpaths, mastering geometric dimensioning and tolerancing, or GD&T, is just, well, it's non-negotiable. Today, we're going to dive right in and see exactly how GD&T transforms engineering ambiguity into absolute profitable precision. Okay, let's take a quick look at our roadmap for today. We've got 4 main stops. First, why we actually need GD&T. Second, anchoring parts with datums. Third, we'll look at key geometric controls. And finally, mastering material conditions. All right, Section 1, why we need GD&T. Let's explore exactly why relying on conventional dimensions causes so many headaches and assembly failures on the shop floor. So the core problem is literally in the geometry. As you can see, conventional coordinate tolerancing relies on standard X and Y limits, right? And that creates a square tolerance zone. But think about it, that leaves massive ambiguity in the corners, and it completely fails to reflect how cylindrical parts actually fit together in the real world. GD&T fixes this. It shifts us away from that ambiguous square and gives us a functional, mathematically precise engineering language. And honestly, if you take nothing else away, look at this number, 57%. Moving to GD&T's circular true position tolerance zone gives a machinist exactly 57% more workable area than a traditional square zone. I mean, out on the shop floor, that translates to a massive reduction in scrap. You're giving them a bigger target to hit, which directly boosts the bottom line, simply by correcting the shape of the tolerance zone. Now, we can't talk GD&T without mentioning rule number 1 of the ASME Y14.5 standard, also known as the envelope principle. It dictates that a feature of size must have perfect form at its maximum material condition, or MMC. Basically, this default rule is your guarantee. It ensures a part is actually going to physically fit and function at its absolute worst-case manufacturing limits, and that's before we even start applying other geometric tolerances. Okay, moving right along to Section 2, anchoring with datums. Now that we understand functional zones, let's look at how we lock these theoretical concepts into physical reality. We really have to strictly separate these two terms because honestly, they get confused all the time in the industry. A datum is a theoretically perfect point accessor plane. It's perfect. It only exists in math and inside your CAD software. A datum feature, on the other hand, that's the imperfect, tangible physical surface on your actual manufactured part. It's what you literally clamp down or touch with a probe during inspection. So, how do we bridge the gap between perfect theory and imperfect reality? Well, quality inspectors rely on datum simulators. We're talking about high-precision physical tools here, like those perfectly calibrated granite slabs, gauge pins, angle plates, or even computer-generated planes from your CMM. These tools are used to physically simulate those theoretically perfect datums right there on the shop floor. And when we use them together, we establish a datum reference frame to completely lock down a part's 6 degrees of freedom in 3D space. Step 1, you restrict the z-axis by resting the part flat on its primary datum. Step 2, restrict X and Y translation by pushing it against the secondary datum. And finally, Step 3, restrict any leftover rotation against the tertiary datum. Boom. It is the exact mathematical equivalent of locking a workpiece securely into a CNC mill. All right, our part is locked down. Let's jump into Section 3, key geometric controls, where we actually apply our manufacturing limits. This table breaks down 3 of the heavy hitters in GD&T and how we measure them in the real world. You've got true position, which controls 3D coordinate variation and is usually mapped by a CMM. Then there's runout, a 2D circular tolerance specifically for rotating parts, often checked right on the floor with a V-block and a dial indicator. And lastly, profile, which establishes a super powerful 3D tolerance zone for complex free-form surfaces. Let's zoom in on runout for a second. It is an absolute necessity for fast-rotating components. Think automotive axles, gears, or drill bits. It controls the total variation a reference surface has when the part is rotated around a datum's true axis. It is so much better at managing wobble and vibration than trying to measure straightness and roundness as 2 separate things. It's a total game changer for rotating parts. Now, for locating features of size, like complex bolt hole patterns, true position is your ultimate go-to control. It specifies a 3D cylindrical tolerance zone that's anchored by theoretically exact basic dimensions. And because this cylindrical zone extends entirely through the thickness of the part, it pretty much guarantees that your mating fasteners will always slide through perfectly. No more forcing bolts to fit.
Okay, quick pro tip here from the manufacturing experts. Stay away from concentricity if you can. It is incredibly difficult to machine and a massive headache for the metrology guys to inspect simply because it requires deriving theoretical median points. Look, in almost all cases, you can achieve the exact same functional requirements by just using true position or runout, completely avoiding all those unnecessary manufacturing costs.
Let's hit our final stop. Section 4, Mastering Material Conditions. This is really the secret sauce for unlocking hidden tolerances and saving some serious cash. The absolute most crucial concept here is maximum material condition, or MMC. This is the condition where a feature contains the maximum amount of material allowed by its size tolerance. So think of the smallest acceptable hole or the largest acceptable pin. Calling out MMC in your drawings guarantees that two mating parts are never going to interfere during a clearance fit, even at their absolute worst acceptable limits. And here is the magic formula for saving perfectly functional parts from the scrap bin. Bonus tolerance equals the measured hole size minus the MMC hole size. Imagine you're on the shop floor and a CNC machinist drills a hole slightly larger than its MMC limit, but it's still within its acceptable size range. Well, they just mathematically unlocked bonus tolerance. This automatically widens the positional tolerance, giving the machinist extra breathing room while still guaranteeing a perfect fit. By combining dimensional and geometric tolerances at MMC, we create this maximum envelope known as the virtual condition. And this is awesome because it allows production lines to use hard go gauges. A go gauge physically simulates that worst-case mating boundary, so inspectors can literally do lightning-fast, pass-or-fail physical checks right there on the assembly line without having to rely on complex CMM programming. If the gauge goes in, the part is good. Simple as that. But you've got to keep your material condition modifier straight. We know MMC grants bonus tolerance for clearance fits. There's also LMC, or least material condition, which is absolutely critical when you need to preserve minimum wall thickness. But here's the catch. If MMC or LMC aren't specifically called out, the ASME standard automatically defaults to RFS, regardless of feature size. RFS grants absolutely zero bonus tolerance. It's super strict, but sometimes that's exactly what highly critical, rigid designs demand. To wrap up our explainer today, I really want to leave you with a provocative thought. Consider this the next time you're drafting a mechanical drawing or chucking a part into a mill. If you are still relying on conventional coordinate dimensions, how much usable tolerance, and more importantly, how much company money are you just throwing away, simply because your tolerance zone is square instead of circular? Think about it.